so we're going to have our t-shirt design for Mesa pretty soon. So,
Beautiful.
Thank you.
It's running, right?
Now we're going to get started.
Yep.
Today we have Mr. Hyatt here and his wife, and his wife is a dental student at the Rosemont University, and she's going to be helping him today. He works for Autobach, and they do stuff, so you guys can see on the table behind me. So I'm going to let him get started.
Well, welcome everybody. Thanks for coming to the talk today. Appreciate it. I'm from Autobach Healthcare, and we're in the business of making prosthetics. We make artificial hands and arms, wheelchairs, all kinds of stuff like that. So my talk today is going to be challenges in prosthetic hand design. I heard that you guys came up with your own hand. You're starting working on one, and I was just telling you guys that I actually, looks exactly like the very first hand that I built out of cardboard and straws and shrink wrap, and so that's a great way actually to get started. And I like the way you think. You didn't make it too fancy, so that's the way you should do it. So I'm a mechatronics engineer, and mechatronics is a combination of hardware and software and mechanical engineering. And I've been an engineer for a very, very long time. So this is Disco Craig back in about 1983 or 2 or something. And this is me. You can see I haven't changed a lot. So a little bit about the company itself. Autobach was founded back in 1919. And this guy's name is actually Otto Bach. And so he's the guy that founded the company, and he was originally making, he saw there was a need for wooden legs and prostheses for World War I veterans who had been injured and lost limbs. So he started this company, and they carved the limbs out of wood and that sort of stuff, but he sort of put it into a factory. Instead of having every single one custom made, he did it in a factory. And so now we're this huge worldwide, I think we're in like 70 different countries now, and we're a huge company, and a whole lot of research, really advanced research and development. I'm going to talk about some of it. And of course, we also manufacture prosthetics. What I really want to encourage you to do today is to begin thinking like a scientist. And I guess there's a lot of definition for how a scientist thinks. I mean, you can think of lots of different ways. But the way I personally do it is that I come up with a lot of questions. I don't just stop with, okay, we made a hand, and how's the hand going to work? I back up from there. Well, how are you going to hook the hand to the guy's arm? What if it gets wet? Can I pick up a banana without crushing it in the hand, and that kind of stuff. So and then I started imagining. Once I asked the questions, I began trying to imagine what the answers would be. How would I solve? And you see all of those problems up there that I've listed. Those are all potential problems if you were just designing a hand. These are all the kind of things that you might have problems with. So for example, picking up a piece of fruit without breaking it. You take this for granted that you can hold a banana like this, but you think about it. You got to pick it up. You got to apply just enough pressure that you don't squash it. But if you apply too little pressure, it just falls out of your hand, or it'll slip. So you have sensors in your hand and in your fingertips that can tell if the banana is slipping through your grip. So you apply just enough pressure, but not too much. And that's a very tricky thing. You may not realize you're doing that without thinking about it. The other thing that happens is, for example, you can reach down and grab a banana. See, I'm not even looking at the banana. I kind of remember where the banana is. Let me turn around once. And I'm a little dizzy. I missed it. There's the banana right there. But I can pretty much, if you're sitting there eating with your friends or something, you're just taking forkfuls. You don't have to look at where your hand is. And that is called proprioception. It's a big word, proprioception. So that enables you to pick up the banana without looking at it, to peel the banana without looking at it, and then to eat it without looking at it. You can go right straight to your mouth, and you think about it. It's all automatic, and it just goes right to your mouth like that, and you can take a bite of it. And you don't think about it, but actually, proprioception has a real, even a really dramatic medical impact. I can tell you a little story. A couple of weeks ago, I went in the doctor for my checkup, right? So I said, Doc, I'm kind of weak. I'm pale. I don't have any energy. I'm losing weight. I don't get it. So you know how the doctor pulls the little light out. So he looks in my ear, up my nose. Just gives me. It only takes him like maybe 30 seconds. He goes, "Well, Craig, I think I can tell you what's wrong. I can help you out, son." And I go, "Well, what's the problem?" He goes, "You're not. I can see like in your left nostril, you've got a bunch of chopped up carrots in there, and I can see some peas and corn you jammed up your nose." And you got some mashed potatoes in your hair. Son, you're not eating right. Are you sure you're the smart kids?
Yeah, I'm pretty smart at times.
So today, what I'm basically trying to get you to do is to think back past the small picture and into the big picture. So here's the big picture with cosmetics. You're not just, with prosthetics, you're not just stopping with the hand itself, you're thinking about the cosmesis, which is the cover on the hand. You're thinking about some type of an adapter. You're thinking about the prosthetic, which is the hand itself, and you're thinking about the socket, which is what hooks the hand up to the person's body. So for example, if I pick this one up, this is a good one. So this right here is the socket, and you don't think about it, but the guy had his hand chopped off or something, right? So he's got to put his residual limb inside of this, so this is what holds it to his body, this part right here. And then there's usually some type of an adapter, because a lot of times you can take the hand off or whatever. I'll show you later. And then you've got the prosthetic itself. And then usually on top of that, so you don't scare little babies, there's a rubber hand of some sort that covers it up. Because you don't want to walk around looking like the Terminator.
That would be amazing.
You guys would rather look like okay. Me too, to be honest with you. And some of the prostheses, this is a cosmetic hand. It doesn't do anything, it's just a piece of rubber, but it's very, very realistic. And I know a guy who wears one of these, he's one of my buddies in Germany. It amazes me how much he can do with it. He can use a mouse. This is just a piece of rubber. It's just a solid rubber. But he can use a mouse, he can open doors, he can do all kinds of stuff with it. So, you don't have to have a lot of fancy motors and batteries and stuff to make something useful. And you'll see throughout this talk that I'm really fond of acronyms. So this spells CAPS, which is why I have caps on top of the letters. Oh. So that's how you can remember things. That's how I remember things anyway.
Caps lock.
So this is a guy cracking a safe, and what do we have? Safes. Got it?
Safes.
So part of the challenge with designing a prosthetic is you've got to have space for stuff. And actually, this isn't totally intuitive. Like when you start designing a prosthetic, you might just think this is the arm. But as I said, remember, the guy's amputated limb, his residual limb, has to go inside of this and will fill the whole thing up, or maybe half of it. So then the question is, where are you going to put all the batteries and electronics and stuff, right? And the next thing is, if that's true, there won't be any room for any motors down here either. All the motors are going to have to be in your hand. But these are the kind of things that, this is where space comes into play.
I like space.
So the next thing you have to worry about is, you've got to attach the hand firmly to the limb. So, one moment.
Chug.
So you have to attach it, and the reason for that is that when you apply a force to the end of the limb, let's say I were to pick up this banana, for example, I would feel some weight when I pick the banana up, but the only way I feel it, I don't have any sensors like a biological hand, I would just feel the force of the socket pushing against my residual limb. Does that make sense to you?
Yes.
All right? you fail. So the residual limb so the socket itself acts like a lever and applies force to my residual limb. That's the only way I have any proprioception. That's the only way I have any sense of what's happening.
Proprioception?
Can you repeat that once again?
Proprioception?
Very good.
Yay!
So it's important that you have to give the man a hand. He got proprioception. So you guys are great. So that's why it's important to have a snug fit. Otherwise, when you pick up the banana, the whole socket moves, and then you begin to feel it, right? If it's too floppy on there, so it's got to be nice and snug. So the next thing is function. The function is, you notice perhaps that some fingers are missing on this hand. It only has really three fingers, kind of almost acting like two fingers, like a pincher. So it doesn't have very many degrees of freedom, whereas your hand can move in all kinds of different ways. You can bend your wrist, you can conduct a symphony, all kinds of stuff. So that's a very important consideration. And of course, the more degrees of freedom, the more way you can move your hand, the more motors and other kind of processing you have to have in there. The next one is ergonomics. So for example, you don't think about it, right? But let's suppose you were wearing this cover over on top of this hand. You're going out and working in the garden, and oops, you hit your hand with a hoe and rip it. So with your hand, you just slap on a Band-Aid, and in a week or two, you're good as new. With this one, you got to buy another piece of rubber for $1,000 or whatever they cost, right? So that's something to think about when you're designing a hand. It's got to be durable. Are you going to clean it? What happens if you rip it? All those kind of questions. And so the nice thing about human skin is it's constantly repairing itself, but this doesn't repair itself. So the questions like that. And finally, the last thing to think about is where you're going to put the sensors to control the hand. And we'll talk about this in a minute, but there has to be something where you can command the hand to open and close and whatnot. So usually that's done by picking up little signals from your muscles that tell the hand to open and close. But the question is where you're going to put the sensors, how many, and that kind of stuff. So the first question was space, and I'm just going to go through each of the points from the last slide one by one and just give you some ideas. So for example, as I mentioned, the residual limb had to fill up the entire inside of the socket, so you can't put any batteries or anything in there. I think on this one, they have a kind of a thin battery on it. The battery is right here, and it's maybe about ½ an inch thick, so that leaves all the other space inside the socket. There should be enough for the person's residual limb. And of course, if you want the arm to work, you'd like the arm to work all day long, so you charge it up overnight. This sounds really freaky that you're charging your arm up or something, but you have to, right? So you charge it up overnight, you wake up in the morning, you start working with it, but you don't want the battery to die, like say while you're driving down the highway or something like that, and your hand freezes up. Oh, no. And the other thing about space was, I mentioned, was the motor's got to be in the hand. There's no room for them in this part where your limb is. And last of all, let me see if I can take this one off. I'm going to put the mic down.
If you don't like that hand, I want to be the Terminator. I want to be Captain Hook.
Let's see if we can crush it.
Can I be Captain Hook?
I'm going to see if I can crush this can. I don't know. Is it doing it? There it goes. Oh, yeah.
Oh yeah.
Crushing the can.
That's what's up. Where's the explosion?
Stop that. There it goes. This is pretty strong one right here. I think this is like some kind of industrial strength hand. I don't know what they use it for actually. But it is. But if I had a hand, it would be this one. Thank you, Joe. So anyway, so that you notice I pop one hand. That can be kind of cool actually. You pop on a hand with a screwdriver or something. Kind of awesome.
Yeah.
Tokyo Gore Police, machine guns.
Get like some.
So the next thing I mentioned was how did that get up there? Word of the day, proprioception. Anyway, so as I mentioned, the other things that people sometimes have trouble with is when they're wearing their prosthetic. They have, as I said, they have a hollow socket that goes over the residual limb, but then during the day they get hot and sweaty. Ew! They get hot and sweaty, and the oil from their skin. These are the kind of things you just got to think about, but you don't ordinarily. So it's very hot inside of there, and then you're walking down the street, and all of a sudden, poof! Your hand slips off. And you got to go back and pick it up. This happens. I've seen a guy kick his leg off, like that. It happens, So you have to, there's all kinds of ways for handling that. Sometimes we create a vacuum inside. Sometimes we use just strips of silicone for friction. Sometimes we use strap like the pirates. You see the pirate hand over here with a hook on it. It looks really sharp. But they just use straps. That is really sharp. That's why a lot of pirates wind up wearing that eye patch. Arr! Oh, there goes another eye.
27
And the last thing we have to talk about is the function. The function is how many ways can the hand move? Can the fingers and everything move? And also how precise is it? And is it powerful enough to crush a can? Is it powerful enough to be useful during the day? And the human hand has 27 bones. Mine has 28, I counted them. And then there's 33 muscles. There's 22 different ways it can move. And it has 10,000 sensors in it. And so those sensors are quite an interesting thing to think about. They can sense heat, they can sense pressure, they can sense cold, they can sense when you hit your hand with a hammer, they can sense the stress on the muscles and joints. So if you try to bend your hand too far, you'll stop bending it before you break a bone or something. So there's all these sensors in there. And typically prosthetic hands do not have those sensors. That's a very advanced thing to put it up. That's just now it's happening in this century. And then ergonomics gets to the, how usable is the hand. By the way, this is my buddy from Germany right here. His name is Martin Rieger.
He's German?
He is German. You can tell, can't you?
German, yeah.
This hand right here is a cosmetic hand. Well, actually, he must be wearing a prosthetic with a motor in it. Catch the frisbee. Otherwise, it would be really, really hard. So he catches the frisbee with it. So that means but you think about that, now what's the next thing going to happen? He's going to land in the sand.
Face plant.
Big face plant, and possibly a hand plant too. And then he'll need a hand transplant for the hand plant.
That's a cool story. Cool story, bro.
Cool story, bro. So what that gets to is how durable a hand has to be. It's not like you can play sports or something and every 2 minutes you're, time out, I broke my hand again. You just can't do that. So the hand has to be durable. It has to look reasonably good, assuming you're not us guys in this room and like this one better. But most people would rather have one that doesn't scare little babies and stuff, and they just want to look kind of normal.
I want to scare little babies.
I know you do. So, and the other thing that's important is part of the ergonomics of the hand is that it does what you want it to do. So if I reach for the banana and I do something to command my hand to close on the banana, if it doesn't close and I reach up like this again, I'm going to be very disappointed. I didn't do it. I want my hand to close when I tell it to close so that I won't be sad. So it's important that your hand does what you expect it to do. It behaves in a way that's reliable. So that's a very important part of design. And so, for example, let's just give one example. If you have the little electrodes controlling your hand and one of them slips out of position a little bit, for example, well, then you might flex the muscle that's supposed to be triggering that, and then nothing happens, and you can't pick up your banana. So that's why it's important to have very repeatable operation, and it has to work all day long. It can't be flaky. And when I say all day long, I mean all day long.
24 hours?
Does somebody have a question?
Why don't you just use the other hand?
What if they're a double amputee? You don't think about that?
I'm going home now.
Bye, mister.
This is the start of this whole business. Thank you.
Thank you, Cappy.
We need to hire that boy. Why don't you just use the other hand?
I'll play basketball with one hand.
So the last topic I'm going to talk about are the sensors that are in the hand. And the sensors are little, I'm going to show you later in more detail, but they're these little devices. They look exactly like this, only way smaller. And they pick up signals from your muscle. So like when you flex the muscle, you know, like calm down. It generates about 1,000th of a volt, a little signal 1,000th of a volt at the surface of your skin. By the time it gets to the muscle, it's attenuated. So then you have to pick up that the little sensor picks that up, and it looks like a lot of noise like that when you flex the muscle. There's a lot of, it looks like fuzz. You see the fuzz. And so you have to clean that, filter all that out, amplify it maybe 1,000 times or something like that, and then you get a nice clean signal. And so that's where the converting to digital 0 and 1. So when it's low, it's a 0, and when it's high, it's a 1. So that turns it into computer language, and then you send that to the motor processor, and then that opens and closes the hand. So as I mentioned before, if you get dirt, or sweat, or the sensor moves around, or the pressure on it changes, that kind of stuff, it causes the sensor to not give a reliable signal, and then you can't pick up your banana anymore. It's unreliable. So, I guess, one of the goals of maybe far in the future, I don't know if it'll happen when you guys are even still alive. Sure, it won't happen while I'm still alive. So the idea is to make a Luke Skywalker hand. How many people have you ever heard of Star Wars? Have you heard? So far, you really do know your world history, don't you? Your father, Luke. Absolutely, you guys are great. You really know your history. So this was a very famous movie when I was a young lad, and they had a scene in there. Battery or something. So where Luke gets his hand chopped off with one of the lightsabers, and where a robot is putting his hand back on, and then he waves his hand and everything, and it's all back to normal. And it looks just like a human hand and everything.
Thanks.
So, it's not real, in case you didn't figure that out.
Are
So,
lightsabers real?
I'm going to show you a movie in a second that'll show that we're getting there. We've got a long way to go. So this, for example, is what's called a cortical implant. It is not a hat. It has little electrodes that actually go down to her and pick up signals from the neurons in her brain. Think about that for a second. And she's using her brain to control this robot and tell her to give her a cup of juice or something.
That's cool.
Pretty awesome. And another idea is, I don't know if you can really see it, but this guy's arm is chopped off right at his shoulder. But he gets these little electrodes planted in various muscles around his chest, and they pick up signals that tell his hand to do different things, like bend his elbow, bend his thumb, all that kind of stuff. Open, close, make a fist. I'm going to show you a movie of that, and it's pretty cool. This is developed by DARPA, which is the defense agency that does really advanced research and stuff. So I can show you that. So, but you have to think about, this dude is controlling his elbow, his wrist, his fingers. This is a robotic hand. I think it probably goes all the way, I can't tell if it goes all the way up to his shoulder, but you think about what's happening in that hand. And watch him, he does his wrist a little bit, he can adjust his wrist.
That's cool.
That's pretty rad. Yeah. So that's far in the future. All right. So now I'm going to do a little demo. What I want to show you with this demo is we've been talking about sensors and you know, and it seems you might think it's something really, really scientific and difficult, but I want to show you that you can buy all the stuff you need to make a sensor and do a little demo. And this is all the software it needs to make it happen. This is the software that's in my little demo here. And I'm going to sneak in a little computer science lesson. So I need a volunteer. Can you come help me?
No, Cappy.
I'm going to need to hot glue this sensor on. It might sting a little. No, it's not. Have a seat right here. Put this armband on there. Now, one thing
So first flex your wrist. So you flex it, you feel a lot of big muscle. So this first wrist, make a fist.
just like that. You feel the muscle bulging out right now? Okay, so put your finger on that. And now I'll put my yes. Okay.